In this video, we're going to talk about solving exponential and logarithmic equations. So when I'm talking about an exponential equation, I'm talking about an equation involving at least one variable in the exponent. So something as simple as 7 to the x power equal to 49 would be an exponential equation. But also things like 1,200 is equal to 300 times the quantity 1 plus 0.05 over 12 raised to the 12t is also an exponential equation because the variable of t is in the exponent in the second equation. The variable of x is in the exponent of the first equation. When I'm talking about a logarithmic equation, I'm talking about an equation where at least one variable is in the argument of the logarithm. So for instance, if I have log base 2 of 3x plus 1 is equal to 6, that's a logarithmic equation because there's an x inside of the argument of the logarithm. Now, when we're talking about an exponential equation, the first rules we're going to look at are the rules with same bases. Now, in all of these examples, I'm going to assume that the base is positive and not equal to 1. If that is the case, then if I have b to the power x is equal to b to the power y, then x is equal to y. And the reverse will also be true. If x is equal to y, then b raised to the x power is equal to b raised to the y power. This phrase, if and only if, means both ways work. If this one is true, then this one is. So if the first is true, then the second is. If the second is true, then the first is as well. In a similar way, with solving with the same base, we can solve with the same base or with the same exponent or with the same argument as long as we assume that all of the bases we're dealing with are positive and not equal to 1. So if I have a to the x power is equal to b to the x power, that's going to happen if and only if a is equal to b. That is for all x's. Okay, I'm not talking about a specific x like 0. I'm saying 4 x's. Or in fact, that would work as long as x is positive and not equal, well, could be equal to 1 as well. So we'll assume that the x's are also positive. The arguments are also positive. Similar with the log equations. If log base b of x is equal to log base b of y, this happens if and only if x is equal to y. Again, we're assuming x and y are positive, the base is positive, and the bases are not equal to 1. Same thing here. If I have log base a of x is equal to log base b of x, that's going to happen if and only if a is equal to b. Again, I'm assuming x here is positive. So we get some very natural ways to solve exponential and logarithmic equations with these rules. With these rules here, we get some nice solving arguments. Let's take an example, a couple of examples on how we could apply that. Here we have two exponential equations. The first one has the same base, the base of 5. So we can solve that using this first rule. Let's go ahead and do that. Since we have the same bases, we set the exponents equal to each other. So 2x minus 1 is going to be equal to 5x plus 11. And then we can use standard rules for solving a linear equation. I would subtract 5x from both sides. That would give me minus 3x minus 1 is equal to 11. And then I'd add 1 to both sides, which would give me a negative 3x is equal to 12. Dividing both sides by negative 3 gives me an x value of negative 4. Now you can check this by plugging in negative 4 into the left-hand side of this equation and plugging in negative 4 into the right-hand side of this equation. If I did that in both cases, I would get 5 to the negative 9th power. So x is equal to negative 4 is the solution to this first equation. We can take advantage of same base rules in other situations as well. While 8 and 2 are not the same base, I can rewrite 8 as 2 raised to the third power. And so by doing that, I can utilize some rules of exponents, namely that 2 raised to the third power raised to the x power is 2 raised to the 3x power. That's equal to 2 raised to the x plus 14 power. And now I can set the exponents equal. Once I have 3x is equal to x plus 14, the solution, or finding the solution rather, is pretty straightforward. Subtract x from both sides, that would give me 2x is equal to 14, and then divide both sides by 2, I would get x equal to 7. And you could calculate that on both sides. 8 raised to the 7th power is 2,097,152. And then 2 raised to the 21st power, because 7 plus 14 would be 21, would give you that exact same number. That is 2,097,152. So again, you can always check your answer by plugging in that 7 on both sides. So that's using the property of same bases, of equality with same bases, means that the exponents have to be equal in two different ways here. You can do similar things with the same exponent argument. You can do similar things with the same argument of logarithms with the same bases. If you want to try this one, go ahead and push pause on the video and try this on your own. Otherwise, I'll do these problems in just a couple of seconds. In this first case, we have the same exponent of 7. Now, I have to be careful that the entire left-hand side is being raised to the 7th power, and the entire right-hand side is being raised to the 7th power in order to do this next trick. But if I do have this scenario, then I can simply set 9x minus 1 equal to 8x plus 8. Then doing my standard solving technique, I would subtract 8 from both sides. That would give me 1x minus 1 is equal to 8. And then I'd add 1 to both sides. And that would give me x is equal to 9. Now, I should make sure that we're not dealing with some weird scenario here. So plug it in. Check your answer. I get 80 raised to the 7th power on the left-hand side and 80 raised to the 7th power on the right-hand side if I plug in 9. So we're good to go on that one. On the next problem, we have log of the same base. Once again, make sure that the entire left-hand side is just log of that base. and the entire right-hand side is log of that base. But if I have this particular scenario, then I can just set the arguments equal to each other. And then solving like we've done before. Subtract 2x from both sides. That would give me 2x minus 1 is equal to 9. Add 1 to both sides. That would give me 2x is equal to 10. And then divide both sides by 2. That would give me x is equal to 5. Now, the one thing I do have to check here, I do have to check that it makes sense to plug in 5. Because remember, when I take the log of anything, the argument inside the logarithm has to be positive in order for it to give me a solution. In this case, that's fine. I get log base 3 of 19 on the left and log base 3 of 19 on the right. And therefore, I do get a legitimate solution because my argument in there is 19 in both cases, which is positive, which is perfectly fine. So that's how we can utilize these same base, same power rules with logarithms and exponential equations. Now, I do want to one more time emphasize this, that the whole entire left-hand side is base to a power. The whole entire right-hand side is base to a power for this thing to work. For us to be able to do this first solving with the same base, or this solving with the same exponent, I need to have that same exponent and it not to be 0, not to be x be 0. Similar here, I need the exact same base on both sides. I need these arguments at both x and y to be positive for this to make sense. Again, here we need x's to be positive for this to make sense. If so, then we can set a equal to b. So the natural question is, what if we don't have that really nice equation form? What if we want to solve an exponential equation where maybe bases differ, or maybe only one side has a variable in the exponent? Well, if we're trying to solve an exponential equation in general, then we can isolate the exponential term and then apply logarithms to both sides. If we do that, then we can apply the properties of logarithms to get my variable, which starts out in an exponent, down into the front of the equation using the power rule of exponents. Let's take a look at an example or two. So first off, let me apply. When I talk about power rules for logarithms, I'm talking about if I take log base b of b to the x, that turns into an x. Or log base b of m to the x power, I can take the x out front. That's what we mean by the power rule. Specifically, this is the power rule, but this is the logarithm exponential inverse property. Again, this is where arguments are greater than 0, base is positive and not equal to 1. So let's do an example here. We have 4 times e to the x power equals 250, and then e to the 3x minus 4 power plus 10 is equal to 1,250. Let's solve each of these by isolating the exponential term, applying an appropriate logarithm to both sides of the equation, and then utilizing one of these two rules. Let's go ahead and do each of these. If you want to try these on your own, push pause on the video. Otherwise, in a couple of seconds, I will do them. All right, in this first case, what I would do, since I have a coefficient on e to the x, I would get rid of that first. So I would divide both sides by 4. That would give me e to the x on the left-hand side, and then 62.5 on the right-hand side. Now, if I apply a logarithm to the left and right, I can use the power rule. In this case, it's actually going to be best to apply the logarithm base e, which is the natural log, to both sides. So if I do that, I get natural log of e to the x is equal to natural log of 62.5. Now on the left-hand side, the inverse property of taking a natural log and then e to the x, the inverse of log an exponential function tells me the left-hand side is x, and the right-hand side is the natural log of 62.5. Now, the natural log of 62.5 is just some real number. It's not a nice real number. It's not a rational number, but it is a nice real number. So this is technically the answer. Many times what we'll do in my class is we'll give the decimal version of that, and that is about 4.14 if I round to 2 decimal places. You can check the answer if you'd like by plugging it in, whether you plug in the exact value into this 4 times e to the x and get exactly 250, or plug in an approximate value and get close to 250. Either way is fine. The key part is we're applying natural log to both sides after I've isolated the e to the x. On this second problem, I need to do a little bit more work in isolating. So what I would do is I'd first subtract 10 from both sides. That would give me e to the 3x minus 4, and then equal to 1,240. Now I don't have a coefficient on e other than the implied 1, so I don't need to divide by that coefficient. At this point, I can apply the natural log to both sides. I get natural log of e to the 3x minus 4 is set equal to the natural log of 1,240. On the left-hand side, inverse property with log and exponential tells me the left-hand side is just 3x minus 4. And then the right-hand side is the number natural log of 1,240. That is a real number. We could get a decimal approximation now, but I'll wait till the end to do that. So at this point, we're not quite done because we have 3x minus 4 is equal to a real number. If I want to figure out what value of x I need, all I need to do is solve for x. Therefore, I'd add 4 to both sides. Be careful when you do that. We're going to add 4. We're not adding it inside of the argument. We're adding it on the outside of the natural log. And then I would be dividing everything by a 3. So I'd have natural log of 1,240 plus 4 and then all of that divided by 3. Be careful that you add the 4 first before you divide by 3. Usually I do it in 2 steps on my calculator. Once I did that, I got approximately 11.12 when I added them. And then I divided that by 3. I got about 3.71. That is rounding to 2 decimal places. Again, you could check your answer by plugging it in into the original x value of your original equation. But that's how we solve things with base e. We take natural log, we isolate the e to the exponent, then take natural log of both sides, inverse property of logarithms and exponential functions allows us to natural log of e to a power to just give me that power. And then I solve from there. Let's try a couple of other problems here. Let's solve these 2 exponential equations. And this one, obviously, we have base e. This one, we have base 10. Go ahead and try that on your own if you want. In a couple of seconds, I'll show you how it's done. All right. On this first one, the first thing we would do is get rid of the coefficient of 500. So we divide both sides by 500. And that would give us e to the 0.07x is equal to 7. That's after I divide both sides by 500. Then I'd take natural log of both sides. Natural log of the left-hand side is going to be natural log of e to the 0.07x. And on the right-hand side, it's going to be natural log of the number 7. On the left-hand side, I simply end up with 0.07x because of the inverse property of log and exponential functions. And that's equal to the right-hand side, which is the real number of natural log of 7. Then I would simply divide both sides by 0.07. So the precise answer is natural log of 7 divided by 0.07. That would be the exact answer. And obviously, most of the time, I would ask for the approximation, which is 27.80 rounded to 2 decimal places. That's how we can solve this exponential function, or equation, excuse me, solve the exponential equation. Let's do this next one. On this next one, I would start out by adding 400 to both sides. If I added 400 to both sides, I'd get 10 to the 2x plus 1 power is equal to 4,900. Now, in this case, we don't have base e. So what I would do is I would take the log base 10 of both sides. If I take log base 10 of the left-hand side, I'm eventually going to get just 2x plus 1. Log base 10 of the right-hand side is log base 10 of 4,900. So the left-hand side becomes 2x plus 1. The right-hand side becomes log of 4,900. Subtract 1 from both sides and then divide by 2. I'm going to do that all in one step. Be careful when you do that because the subtraction has to happen first before you divide both sides by 2. So log of 4,900 minus 1, and then all of that is divided by 2. Now, in order to get this, there is that log base 10 key on the calculator. So all I would do is use that. Make sure that the minus 1 is not in the argument. And then when you divide by 2, make sure that that is also not in the argument. But the x is approximately 1.35, rounding to 2 decimal places. It's always good to check these, plug in about 1.35 into this, multiply that by 2, then add 1, then take 10 to that power, and then subtract 400 and see if you get 4,500. In this case, of course, you do. Again, if you use the exact value on your calculator, you'll get exactly 4,500. If you use approximate value of 1.35, you might get close but not perfect to 4,500. Now, both of these cases in example 4 were pretty nice because E is base E. That's to undo E to a power, I can apply the natural log, which is a key on my calculator. And here I had base 10, so I could apply log base 10, which is also a key on my calculator. If we have other bases, we can do a similar thing, but there's not a direct key on my calculator with base 2 or base 1.04. These two are still doable. We just have to be a little bit clever how I take a log base 2 or a log base 1.04. If you want to try these on your own, obviously push pause on the video. In a couple of seconds, I'll show you how to do these too. In this first equation, we have 2 to the x is equal to 30, excuse me. So what I would do, you can do one of two things. You could, if you'd like, take log base 2 of both sides. That's how I'll solve this first. Log base 2 of the left-hand side is log base 2 of x. On the right-hand side, that would be log base 2 of 30. For the same reason we've looked at before, the inverse property of logarithms and exponential functions or exponential operations, the log base 2 and the 2 to the x would cancel out and just give me an x. So I get x is equal to log base 2 of 30. Now that is just a real number. And if I wanted to calculate it, there's a couple of ways I could get a decimal approximation. One way is if we can do log base 2 on our calculator, then you can do that. You can just calculate with log base 2 if possible. If we don't have that log base 2, then I can do a change of base and say x is equal to the natural log or log base 10, it doesn't really matter, of 30 divided by the natural log or log base 10 of 2. I'm going to do natural logs both in the numerator and denominator. That's my change of base formula. And if I do that, I get about a 4.91. So x is about 4.91 rounded to 2 decimal places. And you can check that out by plugging it in to my original equation. So this is one way. Apply log base 2 to both sides. Another option we could have used is we could have utilized the natural log immediately. I could have taken the natural log of the left-hand side and set that equal to the natural log of the right-hand side. When I do that, instead of using the inverse property, since these two have different bases, this is log base e, and this is base 2 raised to the x power, I could utilize the power rule. I could take that exponent out front, and the left-hand side is x times natural log of 2. The right-hand side is the natural log of 30. Notice what that is. That's x times a real number is equal to another real number. In order to solve for x, I would just need to divide both sides by the natural log of 2. So I get natural log of 30 divided by natural log of 2, which is exactly what I got down here when I took log base 2 of both sides. So either option is going to lead to the correct answer. I can either take log base 2 of both sides, or I could take a natural log of both sides. If I take log base 2 of both sides, I'm using the inverse property of logarithms and exponentials in order to cancel out log base 2 with 2 to the x and just give me an x. If I take natural log of both sides, then the property that I use is the power rule for logarithms, which tells me I can take the exponent out front and then take net times natural log of 2, or whatever base we have. So that's how I can do it. Now we have two options in solving these types of equations, and they're really not much different from each other. Now for the other equation, we take and solve in a very similar way. When I do this, the first thing I would do is I would divide both sides by 1,500. That would give me 1.04 raised to the x power is equal to 8,500 divided by 1,500. If we simplify 8,500 divided by 1,500, we get 17 over 3 as the fraction version of that. And then again, I can take either log base 1.04 of both sides, or I can take natural log of both sides. I think what I'll do is I'll take the natural log of both sides on this one, and then on a future one, I'll probably take a log of that base. So I have natural log of 1.04 raised to the x power is equal to natural log of 17 over 3. Bring that x in front for the power rule of logarithms. I get x times the natural log of 1.04 is equal to the natural log of 17 over 3. Divide by that natural log, divide by the natural log of 1.04, and we would get x is equal to natural log of 17 over 3 divided by natural log of 1.04. That's something I can just type into my calculator if I want. And by doing so, I would get approximately 44.23. So that's what the value of x is. Again, you can check that out by just taking 1,500 multiplied times 1.04 raised to that power and see if you get 8,500. I do get the right answer there. So isolate the exponential piece, apply natural log on both sides, and then solve for x. Let's do a more complicated problem. Let's take 1,200 times 1 times the quantity 1 plus 0.04 over 12. That quantity is being raised to the 12x power, and that's set equal to 30,000. Go ahead and push pause on the video and try to solve this exponential equation. In a couple of seconds, I'll show you how it's done. All right, so let's go ahead and do this. The first thing I would do is divide by 1,200. That is, divide both sides by 1,200. The left-hand side becomes 1 plus 0.04 divided by 12. And that is being raised to the 12x power. The right-hand side would become 25. 30,000 divided by 1,200 is 25. Now what I would do is I would apply a natural log to both sides. You could apply a log base 1 plus 0.04 to the 12 over 12 if you'd like, but it's probably just as easy to apply natural log of both sides. When I do this, be careful what you actually put in parentheses and what you don't put in parentheses. That is important. I'm going to get natural log of that base raised to the 12x power. The 12x power is inside the natural log. And then on the other side, I get the natural log of 25. Now what I can do is I can take the 12x power and set that in front of the natural log using the power rule. Since this 1 plus 0.04 over 12 isn't being raised to any power, or rather, it's implied that it's being raised to the first power, I don't need to write an additional parentheses around that. Now, in order to solve for x, we actually are going to divide two things. I would probably start by dividing the natural log of 1 plus 0.04 over 12. That's just natural log of a number, so don't get thrown off by that. That would give me 12x is equal to the natural log of 25 divided by the natural log of that 1 plus 0.04 divided by 12 number. And then once I get that, then I would divide that whole thing by 12. Now, by doing so, what you can do is you can just simply put 12 in the denominator when you write that. So dividing by a 12, you get natural log of 25 divided by this whole thing. Usually I do this in two steps. I'll do the natural log of 25 divided by this natural log of 1 plus 0.04 over 12. I'd hit enter on my calculator, and then I'd divide by another 12. And usually that turns out a little bit nicer for me when I do it in 2 steps. I ended up with about 80.61 as my answer. Again, if you want to check this, go back up to your original equation and plug that number in for x and see what you get. You should end up with the left-hand side being equal to 30,000. Now, this is solving it using taking a natural log of both sides. We see where this ended up. Once again, at this stage in the second step, if I didn't want to take a natural log, but I noticed that this ugly number, 1 plus 0.04 divided by 12, was my base, I could have, if I'd wanted to, take log of that base So log of that base of that whole number, 1 plus 0.04 divided by 12, raised to the 12x power inside of the argument is equal to log of that ugly base of 25. Using the inverse property of log of a base and base to a power, what that would have given me is that 12x is equal to this right-hand side. Log base 1.04 divided by 12 of 25, of argument 25. So I would have ended up with that. And then I could have said, well, x is equal to that whole thing divided by 12. And if your calculator can do this, if your calculator can use log of any base, then you're perfectly fine in typing this in. We end up getting, again, approximately that same number. These are the same values. So we get 80.61 if I round to 2 decimal places. Once again, plug it in to my original equation if I want to check my answer. So there you go. We have 2 ways that we can solve these log equations, or these exponential equations without really nice bases. We can take natural log of both sides at this stage, or I can take a log of that base 1 plus 0.04 divided by 12 of both sides. Either way is going to lead me to the same solution. Some calculators you won't be able to do this on, so you'd have to use a change of base property. And that change of base property is going to give you the exact thing you got when you took a natural log of both sides. Now, I took a natural log of both sides. You could have just as easily taken log base 10 of both sides and got the exact same answer. So there's multiple options that we can use to solve these exponential equations. Now, what about a general logarithmic equation? In order to solve a logarithmic equation, we are going to isolate the single log on one side, that may take some rewriting so that we actually get a single logarithm on one side of the equation. That single log will have the variables in it. And then either use an exponent on both sides, or we could rewrite this equation as an exponential equation and solve it that way. Both of these two are going to lead to the same outcome. And in fact, after one step, they'll look identical. Now, when I say rewrite, all I'm talking about is realizing that if I take log base b of x is equal to c, then x is equal to b to the c power. That's actually the same thing that I get if I take b to this power is equal to b to this power, and then utilize the inverse property of exponents and logarithms to cancel out b to a power and log base b. That would just give me x equals b to the c power. So the inverse rule for logarithms, you can think of this as applying b to that power on both sides, or you can think of it as rewriting this logarithmic equation into this exponential equation. Either way is fine. So let's go ahead and do a couple of examples. This asks me to solve log base 3 of 2x minus 7 is equal to 5, and 5 times the natural log of x minus 14 is equal to 13. Let's go ahead and solve both of these. If you want to try these on your own, go ahead and push pause on the video. I will show you how both of these problems are done in a couple of seconds. In this first equation, we've isolated the logarithm with the argument in it on the left-hand side already. So I don't need to isolate any more than I already have. I can simply either think of this as taking 3 raised to that log base 3 of 2x minus 7 power equal to 3 to the 5th, or I can think of this as saying, what does this mean as an exponential function? As an exponential function, this would mean that the thing inside my argument, which is 2x minus 7, is equal to 3 to the 5th. Notice that I get the same either way. 3 would cancel out with the exponent of log base 3, and I just get 2x minus 7 on the left-hand side. On the right-hand side, I'm always going to get 3 to the 5th. So I either reimagine this as an exponential function, or I think of it as taking 3 to the power where both sides of this original equation become my exponent. Either way, that's what I end up with. So then I do my standard solving. 3x is equal to 3 to the 5th plus 7. I'd add 7 to both sides. That's going to be 250. Sorry, 3 to the 5th is 243. So add 7 to that, you get 250. And then when you divide by 2, we get x is equal to 125. Now, this I should always plug in and see that it makes sense because I don't want a negative number in the argument. So I should plug this in, make sure it makes sense. When I plug that in, I'm going to get a log base 3 of 243. And that's easily calculated either by a change of base rule, or if your calculator can do a log base 3, calculate that, you will indeed get a 5. So in this case, no problems with plugging it in. We saw that x is equal to 125. Let's do another example here. We have 5 times natural log of x minus 14 is equal to 13. The first thing that I would do is add 14 to both sides. That gives 5 times natural log of x is equal to 27. And then I divide both sides by a 5. Now I'd have natural log of x is set equal to 5.4. That's 27 over 5. I could think of this as raising both, taking e to the natural log of x power and setting it equal to e to the 5.4 power, or just thinking of this as rewriting this as an exponential equation. As an exponential equation, this would say x has to be e raised to the 5.4 power. That's the exact value that you end up with when you solve this equation. The approximate value, the rounded value, is about 221.41. Again, check that out. Make sure that you can plug that in into the natural log argument. And sure enough, you can. Just plug it in, see what happens. 5 times the natural log of that answer, and then minus 14 gives me a 13. So that's how I can solve logarithmic equations. Again, it was just as easy to solve log base 3 as it was with natural log. So the bases aren't nearly as important as they were in the exponential. I mean, they're important for getting the right answer, but they're not as tricky. All right, it's just as easy to take 3 to the 5th power as it is to take e to the 5th power or e to the 5.4 power. All right, let's look at a couple of more complicated equations with logs in them. Here we have log base 3 of x minus log base 3 of 5 is equal to 2. And then we have natural log of x squared is equal to 6. If you want to go ahead and try these on your own, push pause on the video and try these on your own. In a couple of seconds, I'll show you multiple ways of solving both of these problems. All right, in both of these problems, we can actually solve in a couple of different ways. One way we could do this is we could see that this log base 3 of 5 is just a real number. It's going to be an irrational number, but it's a real number. And therefore, we could add that real number to both sides. And we get log base 3 of x is equal to the real number 2 plus log base 3 of 5. If we do this, then we can do the exact same technique we applied before, saying that let's rewrite this as an exponential function. The thing inside my argument would have to be equal to 3 raised to this right-hand side power. So x would have to be equal to 3 raised to this right-hand side power. Now the right-hand side is pretty involved, but it is going to be just a real number. 3 raised to the power 2 plus log base 3 of 5. And again, log base 3 of 5, if you wanted to calculate it using change of base, you could. That would be natural log of 5 divided by natural log of 3. If your calculator has a log base 3 that it can apply, you can apply it that way. And you can get the answer in either way. In this case, it happens to be 45. That is an exact answer, and quite frankly, a very nice exact answer. Okay. By the way, there's a bunch of different ways you can rewrite this as well. You could think of this as 3 raised to the 2 power times 3 raised to the log base 3 of 5 power. And notice that 3 squared is 9. 3 raised to the log base 3 of 5 is 5. 9 times 5 gives us 45. So this one we could do by hand as well if we wanted to. Now that's one option. This option forced me to add log base 3 of 5 to both sides. Another option is to rewrite this left-hand side as a single logarithm using the quotient rule of logarithms. The quotient rule of logarithms says if I take log base 3 of x minus log base 3 of 5, I will get log base 3 of x divided by 5. And then I'd set that equal to 2. If I rewrite this expression as an exponential equation, that would give me x over 5 is equal to 3 squared. So x divided by 5 is equal to 9. If I'd multiply both sides by 5, I'd get x is equal to 45. Either way gives me the answer of 45 that I can plug in and check and make sure I get the right answer for. So either way gives me the correct answer. In this case, probably option 2 was a little bit quicker than option 1. I don't have to deal with this really ugly exponent, but they're very, very similar in that we're using the properties of logs to rewrite and then solve for x. Rewrite as an exponential function and then solve for x. In a similar way, there's a couple of different ways I could solve these two equations. Here we have natural log of x squared is equal to 6. If I wanted to solve it right now, not using any of the properties of logarithms that I know, I could simply say that this means x squared has to be e raised to the 6th power. Now, when I have x squared is equal to e raised to the 6th power, this gives me x is equal to either the positive or the negative square root of e to the 6th. Now, the square root of e to the 6th is e to the 3rd. So I get x equaling e to the 3rd power, or x equaling negative e to the 3rd power. Okay, that would be the option number 1. Now, when I plug in e to the 3rd, since I have to square it before I take the natural log, both the positive e to the 3rd is going to work and the negative e to the 3rd is going to work, because when I take a negative e to the 3rd squared, I get a positive e to the 6th. And that's perfectly fine. Natural log of e to the 6th is equal to 6. We get the right answer. You could get approximate versions of that as well. Now, here's where it gets a little tricky. What if instead of rewriting initially, what if I tried to use the power rule here and pulled out a 2 and then got 2 times the natural log of x is equal to 6? Dividing both sides by 2 would give me a natural log of x is equal to 3, and then rewriting that would give me x is equal to e to the 3rd power. Notice that by going through option number 2, I only get the positive version of e to the 3rd power. There is a reason for that. My power rule works with positive base inside the argument of this logarithm. Let's go back and look at that. When we said log base b of m raised to a power could equal that power times log base b of m, we said that works as long as m is positive. So by doing that rule, our problem was essentially assuming that this base m, in my case, had to be positive. So by doing this rule, taking 2 out front, it was assumed that x had to be the positive version of x. Otherwise, natural log of x doesn't make sense. So if you're utilizing that power rule, note that you're only going to get the positive version of the answer. And we actually need to understand that and then go back up and see, well, could I have also plugged in the negative version of x? And in this case, you could. In some cases, I can't, but in this case, I could as well. So I need to add on the negative version of e to the 3rd power in order to get both of these cases to work. Because in this assumption, we assumed x, my argument, was positive. So obviously on that one, probably option 1 was a bit easier to deal with. In the previous problem, I would say maybe option 2 is a little bit easier to deal with. You don't have to take e to the log base 3 of 5 power or anything like that. But both options will lead to the same answer or same answers if we're cognizant of how those rules of logarithms work. This concludes the video on exponential and logarithmic equations. In particular, we were solving these exponential and logarithmic equations. We saw a number of different ways to do that. We'll use these solving techniques in the next video where we actually solve word problems using exponential and logarithmic functions.